In this video I want to talk about the flow of electric charge. So we'll start off with an example. So we have a cloud up here, thundercloud, and a bunch of negative charge builds up at the bottom of that cloud. And then down here on the ground, that negative charge is going to push all the negatives deeper in the ground and leaving us with positive charges on the surface here. Alright, so we've induced a charge here, and all the negative is deep in the ground and the positives are on the surface. So we have an attraction positive negative here. We have a buildup of charge positive and negative that are attracting each other, and we have some electrical potential energy. So typically we look at the positives as not being the particles that move around much in electric charge flow. So we'll kind of look at this as having an electric potential energy of zero, kind of a zero potential. I can only use the ground for gravitational potential zero. That means the charge that's built up here has some electrical potential energy. Right. Don't know how much it has, but it's got some electric potential energy up here in this case. And so there's the potential for this charge then to move, right, to have a sudden discharge down to the ground here, kind of lightning that takes place. And so that's kind of the idea of electric charge flow. We have to have some electric potential energy between the charges, and then that then will have a tendency to move from one place to the other. Now when it comes to electricity though, we're not so much concerned about just the electric potential energy. We're concerned with how much electric potential energy is there on each charge. So how much electric potential energy does that charge have? How much electric potential energy does that charge have? And so on. So how much energy is associated with each individual amount of charge is what's important when we talk about electric charge flow, instead of just the potential energy by itself. And so as we looked at before, this is just what's known as the electric potential. And the electric potential is often referred to as your voltage. Alright, and so we mentioned this before, it's not exactly voltage, just in terms of electric potential by itself. Here's where we get the idea of voltage. So if I talk about the potential, electric potential here, alright, we call that V, and then down here we would see that since we have no electric potential energy, then we have no electric potential. And so the voltage idea is actually the change in that electric potential. Right, so the V minus V. Right, so that's actually what our voltage is, and so we're finding the difference between the electric potential. So this is also what's known as a potential difference. So the potential difference is what's required in order to have charge flow. So potential difference will cause charge to flow. If you don't have a potential difference between 2 points, then the electric charge is not going to flow. So in the case of the thundercloud and the ground, there's a potential difference between where the charge built up here versus the positive charge built up there, and therefore we can have an actual movement of that electric charge. So this is very uncontrolled, and we want to be able to control it. A good example for kind of looking at how we might put this into something we can kind of see a little bit, because it's hard to see, charges moving. We can take a bucket, right? Got a bunch of water in it, and say we're standing up with it on top of a hill, like that. All right, so here we go. Our bucket of water, and we pour the water out, and so the water comes out and it flows down the hill, right? Okay, the same kind of thing. You have this gravitational potential energy, and the water is able to flow down the hill. Similarly, we have a electric potential energy, or a potential difference between the charges, and the charge then flows from the area of the high electric potential to the area of the low electric potential. Both cases are very uncontrolled. So we want to look at the situation then as we continue with this, where we can control the flow of the charge just like we can control the flow of water instead of just letting it roll down the hill. So here I have a very sad diagram of a water pipe. Right? So here's the pipe right around through here, and so the water comes into your house, right, from some source. So the water, right, comes in through here, flows around, right, through the pipes like so. Right? So you get the water comes in your house, you got the water build up in here, and when that happens you get a lot of water pressure will build up. Right? So remember pressure we've talked about. Right? The amount of force per area. So you get a lot of force per area build up inside here, a lot of pressure builds up inside the actual pipes. Outside the pipe you have just the regular air pressure, which isn't going to be as large, a little bit smaller than the pressure inside the pipes. So most of the time you just have the water just sitting there. In order for the water to start moving around in the pipe, right, so let's go back here. So we got our pipe set up. In order for the water to start flowing in the pipe, right, there has to be an opening. We have to open up a faucet, right? So we have a little faucet right here. Alright, some kind of opening. So we'll open it up, and when we open it up, all that water that's flowing around in here now has somewhere to go. Alright, so the water can flow through here because there's more pressure on the inside, right, or more force, right, on this side here from that pressure, and less force pushing it back in. And so you have a net force that's pushing that way on the water. Right? When it does that, the water then comes out and it lets the water flow. When that happens, the water flows everywhere in the pipe all at the same time. So we want to kind of look at this idea, thinking in terms of water flowing through pipes, as a way to kind of visualize what happens with the electric charge in what we refer to as an electric circuit. So if I look now, I want to talk about an electric circuit. Just like I wanted to control the water, I want to control the electric charge instead of just allowing it to move at random moments and uncontrolled like we looked at in lightning. So I'm just going to draw again a pipe, basically. We'll call it an electric pipe. So here we go. And all this is some kind of conducting material, some kind of conductor. Right, so it's going to be typically a metal. So maybe we just look at this idea instead of it being a water pipe, then that's just a wire. Right, so the simplest thing we would have here is just a wire. Now, in the water pipe example, we had to have the water come in from some source. Since we understand that all the electric charge is already in the atoms, there's electrons and protons, then we know that those electrons, those charges that we're concerned about what's moving around with our electric charge, we talked about charging things up, we talked about the electrons being the particles that would carry the charge. And so we'll put a bunch of electrons already in the wire. Right? So we've already got electrons. There's electrons in here. I'm just not going to draw them in right here. You'll see why in a minute. We're going to add a couple of pieces to this picture. So our wire already has the charge in it. So the wire's there. It's got the charge. It's neutral. Right? There's no electric charge. We have the same number of electrons and protons in the atoms of the wire. And so now we have our wire. Well, we need to give some reason for this charge to flow. And so remember that charge flow is caused by a potential difference that we're talking about here. So potential difference we need to have in there. And remember, another word for that potential difference is voltage. So what we need is we need a voltage source. So we'll put a little box right here. Right? So I need a voltage source. That's what that box is going to represent. That will provide a potential difference. We need something that will provide that potential difference from one side to the other. So there's my voltage source as I look at this. And a voltage source could be a battery. Right? You're familiar with a battery where you plug stuff in. Your phone runs off a battery. And a battery is made up of many cells. We'll talk about that later. It could also be a generator. Right? Like the power company has big generators where they generate the electric energy and the voltage, the potential difference. And so it could be that. It could be a portable generator you might have at home that you can run things off of separate from the house. So some kind of voltage source here. And what that voltage source does essentially is it provides a buildup of charge, positive at one point, negative at a different point. And the whole voltage source is neutral, and somehow, just depending on the different types of voltage sources, there's a separation between where the positive and negative are within the voltage source. So the positive can't get to the negative, they stay separated out. So we have this potential difference. Right? We have an area over here of maybe a high electric potential and a low electric potential. So we have a voltage, we have a potential difference between them. And so since the charge can't go back and forth in here, what happens is all these charges here in the wire then, because of this potential difference, will start to flow. So all the charge then will flow around in the wire itself. All right, so here we have the actual charge flow. And the charge flow is what's known as the electric current. So our voltage source is kind of like our pressure difference. Right? We have a difference in pressure, and for our electricity we have to have a difference in potential. So our voltage source gives that push, and then the electric charge is able to flow around, giving us an electric current. When we talk about electric current, we'll talk about the rate at which it flows. We'll talk about the amount of charge, coulombs, per unit of time, usually seconds. So we'll have a coulomb per second, and that is known as an ampere. Let's symbolize that with a capital A. And that's the unit of current. So it might be flowing here at 4 amperes, so maybe 4 coulombs per second, for example. Now, an interesting item about the charge flow that's taking place. Notice I keep talking about the charge flow, not the electron flow. The electrons really don't move around very much. They're all associated with various atoms and so forth. And within metals, they're kind of free to move around from one to the other. It's kind of like a reservoir, so to speak, of free electrons that can move around. But they don't really move around much. It might be like having marbles in a jar and you shake it up. They kind of move around and vibrate and rattle, but they don't really go anywhere. They might have a slow drift. They might kind of go this way along with it. It may take probably about 3 hours for this electron right here to travel about 1 meter through the wire. So they kind of have a drift speed, but they don't really go anywhere. But the electric field, so remember every electron then, all right, every electric charge, negative charge, has some electric field around it, and that electric field that's associated with each of these electrons then, that is what actually flows. It kind of leans and drifts in the direction of the flow, right, of the potential difference that you have. And so it's the actual electric field. When we talk about the charge flow, you're really talking about the electric field associated with each charge that is actually kind of flowing as you look at that. So we talk in terms of the coulombs, the charge associated in the field, but the electrons themselves are not flowing around through here. Right, so that energy associated with the charges themselves, that electric potential energy we've discussed before, is what then is kind of going to do the work of things. So right now we have what's known as a short circuit. And all the charge is just flowing, but it's not actually doing anything. We're not converting that energy into any other forms, and so it all pretty much just causes the wiring and the voltage source and everything just to heat up from the constant motion without it getting out of the system. It just keeps building up in there. So what we need is to add now an electrical device. So I'm just going to draw a circle right here. All right, and so this is just going to be an electrical device. I know that's a pretty fancy word there, electrical device. So this is anything that will take the electrical energy and convert it, right? Convert the electrical energy into another form of energy. Could be light, could be heat, could be motion, could be sound, anything like that. So it could be a light bulb here, it could be a heater, could be a speaker, anything that's going to convert this electrical energy into some other form of energy. That's the idea here. So now we take the energy as it flows, and these charges do then flow and go through the electrical device. Whereas the voltage source up here, remember I didn't draw electrons in here because the charge doesn't flow through the voltage source. The voltage source is giving that potential difference, right? The pressure difference, or like the water falling down the hill from our water bucket, kind of building an electric hill for so the charge can flow through here. The electrical device, when we look at that, actually provides the last piece of the electricity that we're going to look at, which is the resistance. Right? The electrical device then provides the resistance. It resists the flow of charge, and it uses that energy then. What energy had coming in then is lost to the device to change in another form, and you have less flow as a result. It's a little bit different than water, whereas water, if you put in something in here to slow the flow down, it'll be less speed of the flow on the other side. When you talk about an electric circuit, right, the entire circuit responds to the resistance that's put into it. So maybe before we put a resistor in here, it had that, we said 4 coulombs per second. So maybe now we've got a resistor, maybe it's only 2 coulombs per second, but it's 2 coulombs per second everywhere, because these electric charges are everywhere. The electric field is everywhere. So whatever happens within the circuit affects everywhere within the circuit at the same time. So to wrap this up, here's our basic electric circuit. It has 3 parts. You have a conductor. Right? This provides the electric charge, right, in the form of electrons, basically. You have to have a voltage source, which provides the potential difference, all right, or the voltage difference. And third, you have an electrical device which provides the resistance and converts the energy. So there's your basic electric circuit.